Hi everyone. In today's video, we're going to look into self-supervised method. We're going to look into the papers that contributed to the development of DINOv2. So let's get started. So first of all, what is self-supervised learning? There is a nice paragraph here in this paper. Unsupervised learning of visual features by contrasting cluster assignments. Unsupervised visual representation learning or self-supervised learning. So basically these sound the same thing, unsupervised or self-supervised. Technically, self-supervised or meaning that the neural net is supervising itself for the learning. But by unsupervised, we meaning that we are not feeding any labels to the neural net. Aims to obtaining features without using manual annotations, and it's rapidly closing the performance gap with the supervised pre-training in computer vision. So sometimes it's called unsupervised learning, sometimes it's called supervised learning. But the point is, we are not using any labels to train the neural net. Another important part for the introduction is the categorization of the literature. Most mainstream approaches fall into one of two classes, generative or discriminative. Generative approaches learn to generate or otherwise model pixel in input space. And however, pixel level generation is computationally expensive. So if you're familiar with the generative models, the GANs, basically you train a discriminator and a generator, and the generator tries to generate image for discriminator to make the discriminator more robust and understand visual representations. But the problem with this one is the pixel level generation. So the generator has to generate a whole image pixel by pixel for the discriminator, and this is computationally expensive. So people opted for discriminative approaches that learn representations using objective functions similar to those used for supervised learning. So this is the reason why we are using contrastive learning in these methods, because historically using generative methods is computationally expensive. So these are the papers that I'm going to discuss in this video, and you might be wondering, Mashan, you cannot be serious. Are these the only papers that were published in self-supervised learning for 4 years? No. But in my opinion, these are the papers that contributed the most for the development of DINOv2. Every major component in DINOv2 was borrowed from one of these 5 papers. So let's start with SimCLR. SimCLR is this paper, a simple framework for contrastive learning of visual representations. The major contributions for this paper was the projection head and the augmentations. So we have an image, we make 2 augmentations of the same image, we get the visual representations from the neural net. We got these are the representations, HI and HJ. Then we use a projection head to get the projections and maximize the agreement between the two projections, the two positive pair, and maximize the maximize the disagreement or minimize the agreement between the current view and negative views. So basically, you want the positive views. You want the crops taken from one image as close as possible, and you want the crops taken from different images as far apart. So this is basically contrastive learning. It has been used in graph neural networks. It has been used everywhere. So it's basically minimize the distance between positive views or positive pairs and maximize the distance between negative pairs. And by the way, this algorithm is basically, as someone who worked with similarity matrices, I worked a lot with similarity matrices. This algorithm is basically a piece of art. So let's just break it down and understand what is it. The input is the batch size and constant tau, and the structure of the backbone. They use the component here, and the projection head, and the augmentations. So for all sampled xk and n, so the size is n, do for all k from 1 to n, draw 2 augmentations, and for the first augmentation, get the representations, get the projections, and the second augmentation, you get the representation and you get the projections. For a single view, k, we're getting 2k and 2k minus 1. Now we have to build the similarity matrix, and this is the fun part. So I goes from 1 to 2n and j goes from 1 to 2n. We're computing the similarity. So we have a squared matrix called S, which is 2n by 2n because we have 2 augmentations per sample, and we're defining the loss. The loss is basically the regular contrastive loss, which is the exponent for the positive pair divided by, normalized by the sum of exponents of the negative pairs. Now we're passing, just to make that loss symmetric, we're passing 2k minus 1 as I and 2k as j. Then we're passing 2k as I and 2k minus 1 as j. So we are computing basically the symmetric loss, and we are adding these together. And after computing the loss, we update the networks f and j to minimize L and return the encoder network, because this is what we need, the visual representations, and we throw away the projection head. The sole purpose of projection head is to minimize the loss. Once you're finished with the projection head, you just, as they say in the paper, you throw it away and you take the encoder and you use it for downstream tasks. So I have a visualization for this algorithm in the blog post. Let's start with the architecture of SimCLR. So a sampled mini patch, first augmentation, second augmentation. The augmentation include random crop and resize with random flip, color distortion, and Gaussian blur. Augmented mini batch. Notice that the mini batch has doubled in size because we have 2 augmentation per sample per image. The base encoder was selected to be resonant 50 to we get the representation. The representation are pulled out from the resonate just after the average pooling layer, and the projection head is an MLP with one hidden layer to obtain the projections. So this is the first layer. We're passing the representation to the first layer, and we're getting nonlinearity, real or nonlinearity, and a second layer, just the projection layer. So we're getting the projections, then we're computing the pairwise similarity. So, for example, if the mini patch size was 5, then the size of the similarity matrix will be 10 by 10. And the first 2 rows are 2 augmented views of the first image. So this is the first augmented view of the first image compared to every other single view in the batch. And this is the second augmented view of the first image compared to every other single view in the batch. So these are positive samples representing the similarity between the 2 augmented views of the first image. So the index row 1, column 2 is a positive pair because it's 2 augmented views of the same image. And index row 2, column 1 is another second pair because it compares 2 augmented views of the same image. Everything else is a negative pair. So the individual contrastive loss is calculated for each positive pair of augmented views batch. So this is Sij divided by tau. Tau is the temperature to control the contrastive loss. These are all other negative pairs in the batch. So the similarity score of positive pair is normalized by the sum of exponentials of the similarity score of all negative pairs, and the score of the diagonal is excluded by 1 where k does not equal I. So these diagonal elements are excluded by this indicator function. So if k equals I, then this will be 0 and this whole term will be 0. So we are excluding this element in the diagonal, and this is the positive pair, and everything else is a negative pair that goes into the denominator of this loss function. So the final loss function is the average of individual contrastive losses calculated for each positive pair of augmented views within a batch. So these will be summed together. These will be summed together. So this is the first 2 augmented views of first image, 2 augmented views of second image, 2 augmented views of third image, fourth image, and fifth image. So augmented views will be considered as positive pairs. We're computing the individual loss for these, and we're making the final loss symmetric by adding these 2 together. Another thing to note about SimCLR, because they are one of the first people to introduce the projection head, they have to do extensive analysis on projection head and why it's usable for self-supervised learning. So in appendix, understanding the nonlinear projection head, figure B3, this figure here, shows the eigenvalue distribution of linear projection matrix W, which is of size 2048 and by 2048. This is the size they choose for the linear layer in the projection head. Used to compute Z equals W times H. The matrix has relatively few large eigenvalues, indicating it's approximately low rank. So these are the eigenvalues, and they're talking about a few large eigenvalues. So they're talking about this drop here. So the eigenvalue starts at a very high value, then it drops here. This is a uniform scale, and on a log scale, you could cut here. What does this mean? So I'm familiar with this because this is used a lot in spectral clustering, the eigenvalues and eigenvectors. This means that if a matrix is approximately a low rank, this means that there are fewer clusters and more samples, which is good for self-supervised learning. Because at the end of the day, you want to map images into clusters or map images into classes. And these classes are represented by these eigenvalues. These eigenvalues are not important for clustering. So if you're doing spectral clustering, you could cut here and run k-means and you could find the clusters. You don't have to go all the way and use all the eigenvalues. So I like this analysis. It shows in-depth analysis into why they use the projection head, why they did not compare the visual representations, just pull out the visual representations from the ResNet, from the convolutional net, and just compare them together. That's why they have to pass these visual representations through a projection head. And this projection head, as we will see in the next papers, it becomes a cornerstone into developing self-supervised architectures. From now on, from SimCLR all the way to DINOv2, they all using projection head in different ways, but they all using projection heads. So this is about SimCLR, and it's basically positive pairs and negative pairs are comparing the contrastive loss and after the projection head. But the following works. So this is one of the follow-up works. Bootstrap your own latent and new approach to self-supervised learning. They talked about negative pairs. So they said these methods need careful treatment of negative pairs by either relying on large batch sizes. So this was mentioned in that SimCLR. Here, to keep it simple, we do not train the model with a memory bank. Instead, we vary the training batch size and from 256 to 8,192. So this is a large batch size. By either relying on large batch size, memory banks, or customized mining strategies to retrieve negative pairs. In addition, their performance critically depends on the choices of image augmentations. So basically, they are talking about negative pairs as they need large size, so these are memory requirements, or they are relying on that image augmentation. So how you augment the image, this determines how your neural net will learn the visual representations. But I personally hate negative pairs, and I'll tell you why. So this is a positive view, okay? And these are all negative views. There is no notion of weight. Maybe this augmented view was taken from an image of a car, and there's no guarantee that all other negative views have an image of a car. So if this is image of a car, and this is image of a truck, this is image of a dog, they're all assigned an equal weight. They will be considered as a negative pair, and they all go into the denominator of this loss. We kind of we make it a binary classification task. So with one positive pair, we're saying that this is the same image, but everything else is a negative. I didn't like this idea because it might introduce some bias into the data set. It might break some clusters. It might, I don't know, but assigning equal weights for all negative pairs and treating all negative pairs equally, I didn't like it. So I don't know how it was solved in the literature, but I like the follow-up works, how they just abandoned the idea of negative pairs and just start working with positive pairs, the augmented views. We will see how they abandon the idea of negative pairs. Now we're going to talk about this method, Bootstrap your own latent and new approach to self-supervised learning. So they use another network. This is usually called the momentum encoder, where you stop the gradient on this network and you update based on exponential moving average of the parameters of this network. So the theta parameters for this online network are updated using the stochastic gradient descent, but xi parameters, which is the parameters for the target network, are updated using the exponential moving average. So this is the tau, the temperature that controls the update, and these are the theta parameters multiplied by 1 minus tau. So as you can see, they are still using the projection head from the SimCLR, but they added another network. I have a figure here for this paper. So the input image, first segmentation, second segmentation. This is the target network. This is the online network. View V prime and view V. The encoder was for both networks was selected as resonate 50 to get the representations, and an MLP with one hidden layer and real nonlinearity for the projector to get the projections. And the projector uses the same architecture as the projector. So it's an MLP with one hidden layer. And the target network does not have a predictor. So this is asymmetric design. It's not a symmetric design. We will see later that the self-supervised learning used symmetric design for both networks, but this earlier design, it's asymmetric design. Then we get the projections from the target network and compare them with the predictions from the online network. And the loss was symmetrized by feeding V prime to the online network and V to the target network to distribute the other loss, and we add two losses. So first we run V prime into the target network and V into the online network. Then we run V prime into the online network and V into the target network. Then we add up the losses. So the design of two networks is not new in deep learning, but usually if the two networks are identical, this architecture of two identical networks is called Siamese architecture. So you could trace it back to 1993 with this paper, signature verification using a Siamese time delay neural network. So this is their architecture, two identical network two. So each one will produce a sequence, and they got compared at the end. So I have my own experience with the Siamese networks. So in our paper, this paper refining a k-nearest neighbor graph for computationally efficient spectral clustering, one of the reviewers suggested that we compare to a method called SpectralNet, experiments for integration with SpectralNet. So it was the last experiment. If it's the last experiment, then it was a reviewer suggestion. So the reviewer suggested that we compare with the SpectralNet. So SpectralNet, this is the paper for SpectralNet, spectral clustering using deep neural networks. Let's jump right into the algorithm. So the algorithm, they used a Siamese network. Then they train a SpectralNet for spectral clustering. So spectral clustering, you have to pass the whole thing to get the assignments. What they are suggesting in this paper is just you use a neural net instead of the rigorous spectral clustering pipeline with the same objective as spectral clustering. So here they're forcing the orthogonalization and the gradient step. But we're interested about this part, the training the Siamese net. So in spectral clustering, you need to construct a similarity matrix. And usually this is done using a k-nearest neighbor. But what that's suggesting here is just start with a k-nearest neighbor graph, feed the two samples. If they are positive pair, just choose the distance. If they are negative pair, just make it 0. And maximum here just to avoid the negative value. This is another use of two neural nets, the Siamese nets, in another field other than self-supervised learning. This is unsupervised learning. This is spectral clustering, but they use it differently. They use it to construct the similarity matrix. They use it to avoid using the Euclidean distance. They want a distance that's specific for the data set, and the architecture was largely an MLP. So this was the architecture of the Siamese net. So in our paper, we were suggesting a new graph filtering. We were removing edges from the graph and conducting the rigorous spectral net. So the reviewer suggested that we use our graph as an input to the Siamese net. In the spectral net paper, they used k-nearest neighbor. He suggested that we should try our method. So we tried it out. It got good results, but if you notice that our method has way more edges than the k-nearest neighbor. So this is 12. This is 12,000. Why I'm using a decimal point here but not here? yeah, towards the end of your PhD, you tend to do very strange things. We use more edges than the k-nearest neighbor, so it was basically better off using the k-nearest neighbor than our method. So just to conclude, this is not the point of the video. I'm talking about my own experience with Siamese net, and it can be used in different areas of machine learning. So let's get back to our main topic, and this is the third paper, Unsupervised Learning of Visual Features by Contrasting Cluster Assignments. This paper is usually called SwAV, for swapping assignments between multiple views of the same image. So this method basically has three contributions. They used clustering on top of the projection head, they used the swapped views, and they used multi-crops. We will break these down and discuss them one by one. So first, in contrastive learning, we're getting the projections and we're comparing the projections. What they're suggesting, just assigning the projections into prototypes. And once I read the word prototypes, it just took me back to, and I couldn't find. So most of the papers in the 90s and 80s is behind a paywall. So I have to search archive for this. But this paper came out in 2006, and just to search for prototype. So here they're saying, popular neural algorithms representing data by a small number of typical prototypes, including k-means, the self-organizing map sum, neural gas, and alternatives. Depending on the task in hand, these methods can be used for data compression, data mining, and visualization, nonlinear projection, interpolation, or pre-processing. For supervised learning, k-means directly aims to minimize the quantization error. So the prototypes, usually the term prototype is used as we are mapping samples to prototypes. Usually prototypes are much smaller than the number of samples. So we are mapping samples into prototypes. So cluster centers could be called prototypes. Neurons in self-organizing maps are called prototypes. Neurons in a neural gas are called prototypes. The difference between self-organizing maps and neural gas, self-organizing maps has fixed edges. So you start self-organizing map with edges and you move neurons around with these edges. But in neural gas, you start with no edges and you throw edges as you try to quantize the data. So this was a historical background about the term prototype and how it ended up in this paper. Here, I have a visualization for this method. So basically, they're feeding multi-crops. Multi-crops are global crops are 224 by 224, and local crops are 96 by 96. So you could see here in the paper, they use 2 images of size 224 and 6 images of size 96. But for this visualization, I'm only using the global crops, but the local crops are just the same idea, the same. They're going through the encoder and going through the network. So we pass these global crops into the encoder, and ResNet was selected for this paper to get their representations. Then the projection head, which was a 2-layer MLP to output a tensor of size 128 dimension for the channel dimension, and we get the projections. We compute the scores by multiplying C transpose by Z. Z is the matrix for the projections, and C is the matrix for the prototypes. So this is Z. Z goes from Z1 to ZB. B is the batch size, and this is C. C goes from C1 all the way to CK. K is the number of prototypes. So we're multiplying these together to get the raw scores of the assignments. Then we're computing the probabilities by softmaxing the multiplication. This will give us the predictions. Then they are using sinkhorn normalization to compute the assignments. So sinkhorn normalization is basically this formula here divided by epsilon and normalized by U and V. The point of using sinkhorn normalization is just to enforce that on average, each prototype is selected at least B over K times in the batch. Sinkhorn normalization is an iterative method that makes the rows sum to 1 and columns sum to 1. By using this, we are making the prototypes active. If we didn't do that, some prototypes might die. We do not select them, then the network end up ignoring them. But if we select them early on in the training, even if we select them in a wrong way, the network could adjust itself. But the point is we want to make all prototypes active so we can map images into prototypes. So this procedure here will give us the codes. So these are the predictions, these are the codes, then we're computing the loss between the predictions and the codes. Now let's move to DINOv2 paper. This paper is called Merging Properties in Self-Supervised Vision Transformers. So there are multiple contributions in DINOv2 paper, but most of the work was built on the 3 previous papers. The first contribution of DINOv2 was the use of vision transformers. All previous methods that we discussed in this video have used convolutional neural nets. Specifically, they used the resonant architecture. But this paper used vision transformers. They are saying that self-supervised VIT features explicitly contain the scene layout and, in particular, object boundaries as shown in Figure 1. This information is directly accessible in self-attention modules in the last block. So they are talking about these boundaries. They didn't provide any labels to train the vision transformer, just they used the self-supervised architecture, and they are ending up with these attention maps. Another contribution for DINOv2, they used 2 networks. The first network is called student, and the second network is called teacher. The gradient update is stopped for the teacher network, but the teacher network is updated using the exponential moving average, and the student network is updated using the stochastic gradient descent. I have a visualization for DINOv2 architecture. So again, they're using multi-crops, but here I'm just visualizing the global crops. They're taken from each image 2 global views, and they're feeding these 2 views to the teacher network and to the student network. For both networks, they're using VIT backbone with n by n non-overlapping image patches. The network used either number of patches equals 16 or 8. So we are dividing the global view into 16 by 16 or 8 by 8. So passing these through the VIT encoder to get the presentations, then a projection head, which was consist of the previous architecture, which is N-layer MLP, but they added auto normalization and a prototype layer. So you cast the images into number of prototypes. You assign images into a number of prototypes. But here is another contribution of DINOv2. They are centering the teacher output before comparing it with the student output. So the teacher output will be a moving average of all previous epochs of the teacher, but we are assigning more weight on the most recent epochs. Then we are considering the codes for the teacher as the reference, and we're comparing them for the student, so to compute this loss. Then we're updating the teacher using the exponential moving average. So these are the previous parameters for the teacher multiplied by the momentum, and the parameters for the student multiplied by 1 minus momentum. And the student was updated using the stochastic gradient descent. There are valuable information in the appendix of DINOv2 paper. So for example, here they are testing the number of prototypes. They found that this number gives better results than starting with 1024 or going up all the way to up to 260,000. So that's why they choose this number, and they stick with this number even for DINOv2. Also, for the design of the projection head, this is the previous design without L2 bottleneck. So it's only N-layer MLB. This is the same projection head we saw in SimCLR and SwAV and BYOL. And this is the projection head they proposed in this paper. So they're adding an L2 normalization and a linear layer to map from the bottleneck dimension, which was 256, to the number of prototypes. And they compared these architectures and found that 4-layer with L2 norm bottleneck yields the best performance. If they remove the L2, it won't converge. So these here there are valuable information whether to use batch normalization or not, whether to use GILO or LILO. So they tested different settings and they reported the results in the appendix. Also, they discussed an important topic in self-supervised learning, avoiding collapse. So collapse means that if you train two networks and you want the student to match the teacher, basically the network will say, here you go, this is a constant or this is a uniform distribution. Everything is matched to a constant. This is a collapse. So you don't want that, and you want to make a sense of similarity, but you want to prevent that to avoid the collapse. So here they're saying that the centering that they proposed here, they're talking about this centering for the teacher. Centering prevents one dimension to dominate but encourages collapse to a uniform distribution. In a uniform distribution, everything is the same. You cannot make a distinction. So everything is the same. And while sharpening has the opposite effect, which is one feature dominates other features, they found experimentally that applying both operations balances their effects, which is sufficient to avoid collapse in the presence of a momentum teacher. C here is the centering. You subtract it from the output and you divide by the temperature. C for centering, tau for sharpening. Now let's talk about this paper. This one is called iBOT, Image BERT Pre-Training with Online Tokenizer. The most important contribution of this paper is the masking of patches. So they're suggesting that they kept the augmentations, they kept the two-network architecture. The student network is updated using stochastic gradient descent, and the teacher is updated using exponential moving average. But they are masking some of the patches given to the student, but they're not masking these for the teacher. And they're calculating two losses: the regular loss, which is the class token, and the patch loss that the student has successfully predicted the value inside these patches. The class token loss has a swapped view. To be fair, this architecture was the one used in DINOv2 with little modifications. The DINOv2 paper took this architecture at scale, so they trained on 142 million images. But here in this paper, they are only training on 14 million images. And in the DINOv2, they designed two heads, one head for iBOT loss, which is in here they called patch loss, and the Dino loss, which is computed on the class token. So I have visualization of this architecture. So they're taking global crops and local crops. The global crops are 224 by 224 and the local crops are 98 by 98. So they're taking global crops and local crops. They're passing the global crops just like DINOv1. And DINOv1, I forgot to mention this earlier. In DINOv1, they say all crops are passed through the student while only the global views are passed through the teacher, therefore encouraging local to global correspondences. So this is what they have done in iBOT and in DINOv2, passing two global views to the teacher, masked global views to the student network, and local views. The views are passed the encoder from the vision transformer output. We're pulling the class token and the patch token. And for the student, we're pulling the class token and the patch token also. In iBOT paper, this is the same head for iBOT or for Dino, but in DINOv2, they are separating these for Dino head and iBOT head. They have the same architecture as in DINOv1, which is MLP, L2 normalization, and prototype layer to get the codes. So we're getting the code for class token, for patch token, for class token, and for patch token. Then for the DINO loss, which they called in iBOT paper, they call it the CLS loss. We're comparing the global views in a swapped view, and the local crops are compared with global crops. And for iBOT, because we have the masked tokens, we are trying to see if the student has predicted these tokens successfully. Then we're updating the teacher and the student. Here they have a pseudocode for their method. So U and V are augmentations of X. We perform a block masking for U and V. We're passing U and V for the student network, and we're pulling out the class token and the patch tokens. So doing the same for V. And the same thing, we're passing them to the teacher, and we're pulling the class token and the patch token. For the class loss, which is in DINOv2 is called the DINO loss, we're passing the student with the teacher and the center and making it symmetric by doing the swap view. So in H, we're doing the softmax on the student output. On the teacher output, we're doing the centering by subtracting the C, and sharpening by dividing it by tau, and performing softmax. Then we're returning the loss for the class token. MIM loss, which means masked image. In DINOv2, they call it iBOT loss. We're comparing the patches predicted by the student with the original patch with the teacher, and the patches for the second view predicted by the student with the original patch for the teacher. SGD update for the student, and EMA update for the teacher, and we're updating the center for the teacher. For DINOv2, I already posted the video on DINOv2 architecture. I went through the VIT architecture all the way to DINO loss and iBOT loss. So I'm not going to talk about it, but just to link it with what we talked about earlier. In DINOv2, they use a similar architecture to the iBOT, but they used a larger dataset, and also they separated the head for DINO and iBOT. Also, they trained on full resolution. That's it, guys, for today's video. This was a revision about self-supervised learning methods. I hope this video was helpful. I'll put everything in one blog post and share it with you guys in the description below. Thanks for watching. Bye.